so basically a seed mass black hole. And it's about 3 kiloparsecs from the center. And its dynamical friction timescale, just calculated quickly with the Chandrasekhar formula, is about 10 gigayears. So it's not working its way into the center anytime soon. Yeah?
Do you think that this displacement could also happen with larger galaxies, or is this just the dwarf galaxies that see this?
I think it would happen with larger galaxies, but in that case, the dwarf that's hosting the black hole tends to be the one that's tidally disrupted, and in that case you get sort of a naked wandering black hole in the halo of the larger galaxy, which is something that I will come back to in a bit. So yes, they definitely interact with larger galaxies as well. And that also ends up with off-center black holes. So as a result of this, the black holes in dwarfs do not accrete very much. So what this histogram is showing is the accreted fraction, or basically the fraction of accreted mass of the black hole over its total mass, including the seed mass. So how much gas does it accrete compared to its entire mass? And for the most part, this accreted fraction is 0. The black holes in dwarf galaxies don't accrete much at all. Partly because so many of them are off-center, so there isn't very much to accrete. Partly because even if they are central, there's just not a lot of high surface density of gas available for some reason or another. So even the highest fraction here is like 13% of the mass of the black hole has been accreted by gas. Okay. Which is interesting and useful because that means that dwarf galaxies hosting massive black holes can give us clues to the original black hole seed mass if we assume that they don't accrete. Then we can say, all right, if we see a black hole in a dwarf galaxy, we can estimate that it's that mass of that black hole, if we can measure it, which is difficult, is close to the original seed mass that it formed at billions of years ago. So this is useful information here. I have a story about this. So here's an example. I'll show this plot in a bit. That one of my RE students, Colleen Cleary, made. Here's the star formation history of one of these dwarf galaxies that hosts a black hole. So it starts out kind of bursty, and then it does sort of nothing for a while. And then there's this increase. That's pretty interesting. This bottom plot is the luminosity from accretion of the black hole in this galaxy. And as you can see, it is flat. It does not care that there are bursts of star formation going on. One might think that there's a merger here. You might think that there's this merger going on that leads to this boost in star formation. It would lead to a corresponding increase in black hole accretion. That's something that we think happens. But that only happens if the black hole is in the center. So what this top plot is showing is the radius of the black hole over time. And it starts out in the center, but then it gets kicked out and it's wandering around at a couple of kiloparsecs away from the center. So this black hole does not care that there's a merger and a star formation event going on because it's sitting on the outside looking in at that event going, oh hey, look at that star formation. I'm just going to hang out here and not accrete anything. So that's often what's going on, is that there are star formation events, there are mergers, however, the black hole is not present for them, and so the luminosity of the black hole is very, very low. This was a little alarming to me because I really wanted to find some dwarf AGN in my sample, and there aren't any. So some work I did 2 summers ago with student Jonathan Mercedes Feliz and Chitka Starkenberg at the CCA. We took isolated, idealized dwarf galaxy simulations with black holes and smashed them into other galaxies just to see, can we make a dwarf galaxy with an AGN? And we did. So here's the luminosity of one of these black holes versus time. Here's a just isolated dwarf galaxy. Here's a merger, and then it goes up to above 10 to the 40 ergs per second, which is consistent with the dwarf AGN that are seen. So if you have the right situation where you have either some kind of merger or some kind of perturbation, you can trigger AGN in dwarf galaxies, but it seems that that is a rare phenomenon that has not happened in the cosmological simulations of the sample size that I have. So it can be done, but it's very rare. And the AGN fraction in dwarfs is less than 1%, so it should be rare. There should be very few AGN in dwarfs. Yeah?
2 caveats. One, tidal disruption of stars can still feed those black holes.
Indeed, yes.
And second, if there is a companion star, it can also donate mass to these low mass MBHs.
Yes, that's true, and we are not considering any of that in these
That's right.
simulations.
But
And
in
so,
reality, it can happen.
yes, so that could even be the dominant mechanism for a dwarf galaxy AGN is tidal disruption of companion stars. It's possible.
So when you say that you don't see an AGN, that means that you don't see an AGN at any redshifts.
At any redshifts. Here's how I show this. Here's this nice segue. Thank you. Versus time or versus redshift. Here is the maximum luminosity that any black hole in the simulation reaches. So the circles are all simulated black holes. This is the brightest that they ever get at all redshift from 6 onwards. And the red is where they are at redshift 0. The stars are all observations. So these are some local dwarf AGN. And these are some higher redshift AGN from MARVEL-ous sample here. And you can see that none of them get even close to being observable. None of them are observable AGN except maybe this one here. So I need to look into this one a little bit more. Because possibly this is observable. I need to see what's going on. But so yeah, no, they're low luminosity basically throughout their evolution.
Is there a classification issue with low luminosity AGN that could be dwarf AGN? Or are they really two separate things?
Could low luminosity AGN be dwarf AGN?
Yeah.
I mean, I guess it depends how you're defining.
I just was wondering, you said 1% of dwarfs are AGN, but you have to know that it's a dwarf from AGN to classify it that way. And there could be.
I mean, I guess dwarfs are defined by their stellar mass usually. So whatever their mass is, decide. I don't know. I don't actually know where people just draw the line of what's a dwarf and what's not a dwarf.
So most low luminosity AGNs are in bigger galaxies.
Yeah. Yeah. So yeah, they are. Okay, so if there's hardly any hope for electromagnetically detecting these, how do we detect them? How do we learn about black hole seeds? We use gravitational waves, hopefully. I'm a member of the NASA LISA study team, and I'm very excited about LISA and happy to tell you about it. LISA will launch in 2034, plus or minus, maybe minus.
Minus.
Hopefully minus. I have no control over this and no insider knowledge. I only hear rumors, the same as you. But LISA is going to be a space-based gravitational wave detector that is going to trail Earth in its orbit in a giant cartwheeling triangle. These devices are going to be 2.5 million kilometers apart, which is more than 5 times the Earth-Moon distance. It's huge and it's awesome. And it's definitely going to launch because the technology has been proven with LISA Pathfinder, and ESO is in charge, which means that no matter what happens with NASA, we can't screw it up too bad. It's definitely moving forward. And so LISA will detect gravitational waves from merging massive black holes, similarly to how LIGO does so now, but for stellar mass black holes.
You know what frequencies?
Yeah. So, I have the frequency plot is in my hidden slides, but here I have some masses of binary black holes. So down here in this axis is the total mass of a binary system of black holes, and this is redshift. These colors here represent signal to noise. So this is the signal to noise that can be detected for a binary merger of black holes, which for in this range of like 10 to the 4 to 10 to the 7 is really great all the way up to very high redshifts. Redshifts that we can't really use electromagnetic waves to observe because these are dark ages of the universe. But we can probe structure formation and black hole formation at all the way up to redshift 20 and possibly beyond with LISA if black holes are merging at these times.
But without dynamical friction, how would you make the diamonds? You need to bring them together, right?
Yes.
You need to bring them to close enough such that the coalescence time is less than the Hubble time.
Indeed.
So how do you do that?
Well, we don't know that this will happen. We just say if it happens, we'll find it.
No, I mean, in your simulation, you just
Yeah.
argue that some of them hang around at large distances, but
Right.
you really need to bring them together in order to make
Right.
this.
Well, some of them do come together. That's
Okay.
my next slide. You guys are really great at advertising the next slide. I'm very pleased. Right. So this mass range of 10 to the 4 to 10 to the 7 is like really optimal for LISA. And this is also great because this is right in the intermediate mass black hole range and early black hole growth range that we're interested in probing. Anything more massive is harder to see unless it's very close, but pulsar timing arrays should be able to take this, get this part a little bit better. So there are mergers of black holes in the dwarf galaxies in the simulations, and they are represented by these points here. So this is the same figure, but I've stuck black points for each black hole merger, and there's little numbers here that represent the mass ratio of each black hole merger. So we have some 1 to 1, 1 to 5, 1 to 2, 1 to 3. There are a couple here that you should ignore because I don't actually believe them, but they're there because they're there. But you can see that there are mergers from redshift like 12 and 8, not a redshift 20. And then there are some, I guess you call them lower redshift mergers as well going on. And so these, you should ignore the 1 to 112 and the 1 to 39 because I can explain to you later why I think that those are not real. Those mass ratios are not real. Maybe the mergers are real, but the mass ratios are not real. So most of the mass ratios are between the 20% and 1 to 1. Yeah?
What do you define as a merger? Like, but again,
Aha. Good question, good question. So we definitely ignore a lot of physics. And so basically, when they get close together, as well as have low relative velocities, then we allow them to merge. So there's definitely no gravitational wave timescale. There's no fixing a final parsec problem. Like all of that is swept under not even a rug, but like a mattress.
like, yeah, but instantaneously, like you say, they merge straight away.
But it's essential. The mattress, you have to open up the mattress and see
Yes,
it.
yes.
But it may not happen.
Yes, I do want to open up the mattress, but I think, yes, I totally agree with you. It needs to be open.